We humans have always looked to the skies with wonder. For millennia, the power of flight seemed unattainable, a realm reserved for mythical creatures and gods. Yet in the 20th century, we unlocked this ancient dream, taking to the skies in machines of incredible power and grace. These marvels of engineering known as airplanes are powered by engines that seem to defy gravity itself. But how do these engines, these hearts of metal and fire, actually work? How do they propel massive metal birds across continents and oceans? The answer lies in a symphony of air and fire, a carefully orchestrated dance of pressure and combustion. Airplane engines, specifically the jet engines that power most modern aircraft, are marvels of thermodynamic ingenuity. They take the very air we breathe, and through a series of ingenious steps, transform it into a force powerful enough to overcome drag and propel us across the sky. In this exploration, we'll delve into the heart of these engines, unraveling the mysteries behind their power and efficiency. At their core, jet engines are air-breathing engines. They operate on a simple yet elegant principle: suck in air, compress it, mix it with fuel, ignite the mixture, and then harness the energy released by the expanding gases. This process of continuous combustion generates a powerful thrust, propelling the airplane forward. Imagine a balloon being inflated and then suddenly released. The air rushing out of the nozzle propels the balloon in the opposite direction. Jet engines work on a similar principle, but instead of a one-time burst of air, they create a continuous, controlled explosion that generates constant thrust. To understand the intricacies of this process, we need to break down the engine into its main components: the compressor, the combustor, the turbine, and the exhaust. These four components work together in perfect harmony, each playing a crucial role in transforming air and fuel into thrust. The journey begins with the compressor, the first major component of a jet engine. As the airplane moves forward, air is forced into the engine's intake. This incoming air then encounters a series of rotating blades attached to a central shaft. These blades act like powerful fans, compressing the air and increasing its pressure. Think of a bicycle pump. As you push down on the handle, you're compressing the air inside, making it denser and more resistant to further compression. The compressor's role is crucial because compressing air increases its potential energy. Just as a stretched rubber band stores energy, compressed air contains more energy than air at atmospheric pressure. This stored energy is what will ultimately be released in the combustion chamber to generate thrust. From the compressor, the now highly compressed air enters the combustion chamber, often referred to as the engine's fiery furnace. Here, the magic of combustion takes place. Fuel, typically kerosene-based jet fuel, is injected into the combustion chamber and mixed with the compressed air. This mixture is then ignited by a continuous spark, creating a controlled explosion. The combustion process releases a tremendous amount of energy in the form of heat, causing the air to rapidly expand. Imagine a small explosion happening thousands of times per minute. That's essentially what's happening inside the combustion chamber. This continuous release of energy is what drives the next stage of the engine's operation, the turbine. Section 5. Spinning to life, the turbine's role. Located downstream of the combustion chamber, the turbine's role is to extract energy from the hot, expanding gases produced during combustion. The turbine consists of another set of blades mounted on the same central shaft as the compressor. As the hot gases rush past these blades, they cause the turbine to spin rapidly. This spinning motion is what powers the compressor at the front of the engine. Think of a windmill. The wind's energy causes the blades to spin, and this rotational energy can then be used to power other machinery. In a jet engine, the turbine acts as the windmill, harnessing the energy of the expanding gases to drive the compressor. Section 6. A symphony of power, thrust, and the exhaust. After passing through the turbine, the now much cooler but still expanding gases exit the engine through the exhaust nozzle. This high-velocity exhaust stream is what generates thrust, propelling the airplane forward. Remember Newton's third law of motion? For every action, there is an equal and opposite reaction. As the gases are expelled rearward, they create a forward force on the engine, and thus on the airplane. The faster the gases are expelled, the greater the thrust produced. This is why jet engines are so powerful. They are able to accelerate a massive amount of air to very high speeds, generating tremendous thrust. This completes our journey through the heart of a jet engine. We've seen how air is drawn in, compressed, mixed with fuel, ignited, and then used to generate thrust. It's a testament to human ingenuity, a symphony of air and fire that has revolutionized travel and shrunk our world. Section 7. Efficiency in the air, the bypass ratio. The story of jet engine evolution doesn't end there. Over the decades, engineers have constantly strived to improve the efficiency and performance of these remarkable machines. One key innovation has been the development of turbofan engines, which incorporate a large fan at the front of the engine. This fan bypasses a significant portion of the incoming air around the core of the engine, where combustion takes place. This bypass air serves two important purposes. First, it mixes with the hot exhaust gases, reducing their velocity and noise. Second, it generates additional thrust by being accelerated rearward, similar to how a propeller works. This bypass ratio, the ratio of air bypassing the core to air entering the core, is a key factor in determining a turbofan engine's fuel efficiency and noise levels. Section 8. Technological marvel, the turbofan engine. Modern turbofan engines are marvels of engineering, incorporating advanced materials, sophisticated blade designs, and complex control systems to optimize performance and efficiency. They are capable of generating incredible amounts of thrust, allowing airplanes to reach cruising speeds of over 500 miles per hour and altitudes of over 30,000 feet. The development of the turbofan engine has been instrumental in making air travel more accessible, efficient, and environmentally friendly. These engines have enabled the rise of long-haul flights, connecting distant corners of the globe and transforming our world into a more interconnected place. Section 9. Conclusion. The enduring allure of flight. From the Wright brothers' first tentative flights to the sleek supersonic jets of today, the quest to conquer the skies has driven innovation and captured the human imagination. At the heart of this incredible journey lies the jet engine, a testament to our ingenuity and our insatiable desire to explore the unknown. As we look to the future, we can only marvel at the possibilities that lie ahead. Perhaps one day, we'll develop even more efficient and sustainable engines, allowing us to venture beyond our own planet and explore the vast expanse of space. For now, let us appreciate the wonder of flight, made possible by these marvels of engineering that continue to propel us across the sky.